With a radius of about 70,000 kilometers, Jupiter is the largest planet in the solar system. But how did it get so massive? I'm Eric Malikyte, and today on ScienceGet we're talking about a new study that suggests a shocking reason for Jupiter's size. Since its formation 4.6 billion years ago, Jupiter has defended this planet against otherworldly threats, acting as a gravitational attractor for comets and asteroids that could have changed the course of evolutionary history. Without it, we wouldn't be here today. Since its discovery, scientists have speculated on how the gas giant became so massive. As the solar system was forming, Jupiter was more than likely the first planet to form. But as far as what caused it to get so massive, there are two different theories. One theory is that the gas giant swallowed a lot of quote-unquote pebbles. No, not the kind of pebbles that you might find in your backyard, but rather meteorites around the size of boulders. I have no idea why they call them pebbles in this case, but I don't come up with the terms. But thanks to a new computer model and paper that sources gravitational data from the Galileo and Juno space probes, the idea that pebbles contributed to Jupiter's mass may be obsolete. Figuring out how Jupiter's innards are structured has been a chief concern for scientists. But unlike Earth, where we can use seismic waves to study the mantle and core, Jupiter has no physical surface. But even if it does have a rocky center, it's highly unlikely that there would be any tectonic activity. Most data seems to point to the idea that Jupiter has a solid rocky core around 12 to 45 times the mass of our planet. That core is estimated to reach temperatures of 35,000 degrees Celsius. And if scientists are right and the core is solid, then that solid core is enveloped by a layer of metallic hydrogen. Let's just say that you would never want to be caught falling into Jupiter. Over the years, we have taken a metric ton of photos of Jupiter. Most of these are of its stunning bands of clouds and storms, like the Great Red Spot. Of the 9 probes we've sent to Jupiter, Juno gave us an unprecedented look at the behemoth gas giant, both inside and out. And it is thanks to Juno and partially Galileo that researchers involved with a study published in the journal Astronomy and Astrophysics were able to put together a simulation of Jupiter's formative years. Galileo and Juno gathered a lot of data on Jupiter's gravitational field. And after studying the effects that gravity has on the giant planet, researchers were able to put together a simulation that suggests that not only does Jupiter have way more rocky material in its depths, but that our theories for its structure and formation might be wrong. The second theory of how Jupiter might have expanded to its current size rejects the idea that it got so massive by swallowing boulder-sized meteorites, but rather that it consumed still-forming planets. And it is this theory that this new simulation and study seems to support. Jupiter takes 12 years to orbit the Sun. At key points in that orbit, Juno and Galileo both studied Jupiter's gravitational field, and the researchers involved with the study were able to use those data sets to create gravitational maps of Jupiter's surface, establishing where gravity differs on the planet. What's really interesting about this study is that Jupiter seems to have a surprising amount of heavy elements, like way more than we originally thought. This rocky material exerts a much stronger gravitational pull than the gases in Jupiter's other layers. The models provided by these researchers suggest that Jupiter's core is likely somewhere in the ballpark of 11 and 30 Earth masses, and that heavier materials could make up as much as 9% of the planet's mass. Yamila Miguel, an astrophysicist at Leiden University in the Netherlands, says that the idea that Jupiter accumulated all this mass from smaller meteorites simply can't explain its massive size. This means that Jupiter could only have gotten so massive by consuming planetesimals, the building blocks of planets. In the first couple million years of the solar system's life, the still-forming Jupiter was devouring baby planets. Hypothetically, if Jupiter had formed from smaller, boulder-sized space rocks, then once it had accumulated most of its gaseous layers, it would have stopped absorbing rocky material. However, these new models suggest that Jupiter kept cannibalizing still-forming planets even after it stopped absorbing gas. This actually makes quite a bit of sense in the early chaotic solar system. Since the discovery of exoplanets, and specifically hot Jupiters, it's thought that Jupiter and Saturn had to have formed closer to the Sun and slowly migrated to where they are now. If that's the case, then a forming OG hot Jupiter would have had plenty of material to gobble up on its journey to its current orbit. So, score! We now have a pretty good idea of how Jupiter formed. But we're not done yet. Before this study, it was thought that Jupiter's atmosphere caused a lot of convection that would allow for hotter gas to propagate near the core. This would also make it so hotter gases could rise up to the outer reaches of Jupiter's layers to cool off a bit before taking the plunge back into the planet. But now this doesn't seem to be the case. This study showed us that Jupiter's interior layers don't mix well with its upper gaseous layers. We're talking oil and water here, although that's probably not fully accurate either. So, no convection. This flies in the face of what scientists thought we'd find in Jupiter's core. It seems that the heavier rocky and metallic materials seem to gravitate near the planet's core, sometimes getting mixed up in the lower atmosphere as well. With so much of our understanding surrounding Jupiter changing, it's only natural that our theories for how the rest of the planets in the solar system formed would follow that trend. And while it's going to be a while before new models are produced for the earliest period of the solar system's formation, one thing is certain: we're going to be feeling the after effects of this study for a while. Well, at least all of us space nerds will be. But what do you think? Do you think this new look at Jupiter's insides is a revelation? Or do you think that the researchers missed something? Do you think Jupiter has a solid or liquid core? Comment down below and let me know. If you dug this content, be sure to do all that algorithmic jazz and like, subscribe, ring that bell, and join the Discord where you can meet other science nerds like you. And hey, check out all those wonderful names. Thank you, patrons. I'm Eric Malikyte, and I'll see you next time, Space Cowboy.